Hello everyone, my name is Jakin, and today I'm going to be presenting on Lab 3, which is the effect of size and composition on the properties of renewable copolymers. So I'm doing this with the Materials Engineering and Chemistry and Biochemistry departments at California Polytechnic State University San Luis Obispo, and my partners were Cameron Causey and Miguel Martinez. So for a little bit of background here, ring opening polymerization, which is the polymerization we used, is a type of polymerization in where the cyclic monomer is opened up to form a linear polymer. It's commonly used to produce high molecular weight polymeric materials with unique properties and applications. A cyclic monomer with the strained ring is opened by a nucleophilic attack, which leads to the formation of a linear polymer chain. This reaction is typically initiated by a catalyst or initiator and proceeds through a radical, anionic, or cationic chain growth polymerization, and common examples are E-caprolactone, so generally lactones, lactams, and cyclic esters. In this lab, we focused on an ABA triblock copolymer. ABA triblock copolymers are copolymers consisting of 3 blocks, 2 outer blocks, which are the A blocks, and which are the same monomer, and then a central block, which is called the B block. They can usually be synthesized through a variety of methods, which include living anionic polymerization, ring open polymerization, atom transfer radical polymerization. For anionic polymerization, the central block is synthesized first, followed by the addition of the 2 outer blocks on the end of the central block. In ring opening polymerization, the same thing generally happens, except that the cyclic monomer is used to form the central block, which is opened up usually with an initiator, as you'll see in this experiment, and then it's followed by the addition of the 2 outer blocks. ATRP is a reversible deactivation radical polymerization, in which the deactivation of radicals involves reversible atom transfer or reversible group transfer, catalyzed usually through transition metal complexes. The unique properties of these ABA triblock copolymers arise from the difference in the chemical nature of the A and B blocks. So for example, you can create an ABA triblock copolymer made of hydrophilic A blocks and hydrophobic B blocks, which can assemble into micelles or vesicles in water. These copolymers can also exhibit thermoplastic elastomeric behavior, which means when they can behave molded and shaped like a plastic when heated, but they retain their elasticity when cooled. All these kind of properties allow ABA triblock copolymers to be super attractive for applications such as drug delivery, tissue engineering, soft robotics, adhesives, coatings, and sealants. So one commonly used polymer for ABA triblock copolymers is PLLA. This is a biodegradable, biocompatible polymer. It's often used in the medical field since it's non-toxic and non-immunogenic. It's made usually from lactic acid, which is a naturally occurring substance in the body, and it is a very brittle and stiff polymer, so oftentimes it's added to a softer middle block to add strength and rigidity to a material. So in this experiment, we basically wanted to synthesize an ABA triblock copolymer from naturally occurring δ-dodecalactone and L-lactide monomers. And we wanted to create 2 of these, one of which was a 35 weight percent PLLA block and one of which was a 45 weight percent PLLA block. We then went on to analyze the copolymer and characterize it using FTIR, DSC, NMR, and DMA. So for the method section, we basically synthesized the polymer in a dram vial. We used a 1,4-benzene dimethanol initiator, or BDM, which was added to the δ-dodecalactone monomer, as you can see in this figure here. This would ring open the monomer and it would leave your BDM initiator in the middle. The solution is just then sonicated to dissolve, and then nitrogen is blown so we can take out all the HCl catalyst, which is determined by pH paper. Now to add the A part of the ABA blocks, we used L-lactide. We submerged the vial in an oil bath to let it heat up, and then we added the proper amount as calculated of PLLA, as well as a tin 2-ethylhexanoate catalyst to help dissolve the polymer. After the polymer was added, we added cooled methanol and gravity filtrated. The polymer was then heated in an aluminum pan to create a solid film. Down here we have all of our conditions for how we characterized the polymer using all these machines. And then in figure 2 we have this schematic showing the addition of these two A blocks here and here. So for actual results, we have our FTIR here. FTIR stands for Fourier Transform Infrared Spectroscopy, which identifies chemical bonds by amount of light transmitted through a material. We took FTIRs of both the monomers and the two 35 weight % and 45 weight % polymers. As you can see here, the d-dodecalactone has 2 CH stretching vibration peaks, as does the L-lactide around this area. And then the d-dodecalactone has 1 non-conjugated carbon double bond oxygen stretching vibration here, whereas the L-lactide has 2, one at around 1760 and one at 1730 inverse centimeters. So, as you can see in our C group and D group, our C group, which has less of the L-lactide by weight %, has a smaller peak at around 1760. Whereas the D group has a little bit larger of a peak at around 1760, which is the peak distinguished by L-lactide. So this can kind of confirm that there's probably a larger presence of L-lactide within this 45 weight % polymer. So next we have NMR, which is nuclear and magnetic resonance. This basically allows for the analysis of chemical and physical properties of molecules by measuring their interaction between nuclei and an external magnetic field. So the predicted values for the number average molecular weight, or MN, for the samples C and D, which is 35% weight % and 45 weight %, we found the molecular weights for the polymers to be 36,792 and 43,299. Through actual analysis of these spectra in figure 4, we figured out the actual MN values we got were 33,481, which is pretty close to what was expected, and 24,574, which was a little ways off. We also calculated, using these graphs, the actual % compositions. For C, it was pretty close to the 35 weight % we were looking for L-lactide, and for D, it was a little ways off, hitting 39.1%, whereas we wanted 45 weight %. So here are our DSC graphs. DSC, it stands for differential scanning calorimetry. It's a thermal analysis technique which measures the heat flow in or out of a sample as it is heated and cooled, which gives us information about its thermal properties and behaviors. So one big thing to note in the figures below is that block copolymers C and D had glass transition temperatures at -55 and -60, which are almost exactly on the values that are reported in literature for the glass transition temperatures of d-dodecalactone and PLLA. So that would be the -50, roughly 55 is the d-dodecalactone, and the around 60 Celsius is PLLA. And PLLA's glass transition is generally reported in the 50 to 80 range. C and D also had a melting temperature around 127 on C and around 136 for D, which are slightly lower than the reported literature values of 151 degrees Celsius. This could have something to do with our ramp rates or just the way the copolymer was made. The one thing to note is both of these DSC curves were missing cold crystallization peaks for PLLA, which usually are identified around 116 degrees Celsius. So we're not entirely sure why those aren't present, but we may want to, if we had more time, repeat this experiment again and see if we can identify those peaks. All right, the next characterization was dynamic mechanical analysis. This measures mechanical properties as a function of temperature, frequency, and time, which includes stress strain and modulus. So here we decided to do 2 stress strain curves. Unfortunately, due to time and due to the formation of some of the films, DMA was only run on the 45 weight percent DDDL PLLA triblock copolymer, and it was also ran on a separate group's sample. Or instead of δ-dodecalactone, it was decalactone, and it was also 45 weight percent. So you can see both of those curves here in Figure 6. You can see that the decalactone had a larger Young's modulus than the δ-dodecalactone, which is represented by the steepness of the slopes. You can also see that both copolymers exhibited similar yield strengths, right around that 0.008 megapascals, and that δ-dodecalactone had a higher ultimate tensile strength. One thing to note is that both films, not pictured, but they both had significant void content, probably when the films were heated, then cooled in the aluminum pan. A lot of air bubbles were stuck inside the film, so they had a lot of void content, which kind of hinders the validity of this data. Also, interesting thing to be aware of is that this experiment kind of follows a few principles of Green's chemistry, which is any chemistry that is kind of geared towards sustainability. The main things about this experiment to note is that we used naturally occurring lactones rather than conventional non-renewable petrochemicals. And then we also used L-lactide, which is an eco-friendly monomer derived from plants like corn and sugarcane. And then the copolymerization also occurred without the use of a solvent, thus there was no solvent waste, helping for the kind of sustainability model of this whole experiment. So for conclusions and future work, we were able to successfully synthesize 2 ABA triblock copolymers using renewable monomers L-lactide and δ-dodecalactone. And we confirmed this synthesis using FTIR, NMR, DSE, DMA. FTIR and NMR confirmed the larger presence of PLLA in polymer D than C. However, the actual percent compositions that we were aiming for, which was 35 and 45 weight percent PLLA, were slightly off, instead ending up with 37 roughly and 39. DSE was able to properly identify the glass transition temperature of both monomers. However, they were both missing a cold crystallization peak. And stress strain curves were successfully generated but inaccurate due to high void content. So future work should focus on replicability of the experiment. Unfortunately, due to time, more films were not created, which those films could have then been used, hopefully if they had lower void content, for more accurate DMA results, and to confirm, for some reason, the lack of presence of a cold crystallization peak in the DSE. Samples should also be tested again on NMR to confirm that number average molecular weight values were actually lower than expected and not just a simple analysis error. Future work should also explore property differences at higher and lower PLLA weight percent compositions. The variation in these weight percents would probably give us a better scope of how altering the composition of this triblock copolymer leads to varying properties. Acknowledgements. Thank our lab assistants, who are Sudeep Lewis and Isabel Gomez, for assisting in the project, and just in general, GGSDT and LASCT for continually supporting the Polymers and Coatings department at Cal Poly. All the experimental work was carried out at the Kenneth N. Edwards Western Coatings Technology Center at Cal Poly. And we also thank our instructor, Leslie Hamachi, for the opportunity. And then here are my references. Thank you guys very much for watching. I hope you have a great day. Peace.